Okay, so today we're going to be talking about properties of the definite integral. And when looking about properties of the integral, it's important to remember where the integral comes from. The integral is coming from setting out to find the area between a function and the x-axis from x equals a to x equals b. So we want to find the area of this region in here. Okay, and the way that we did it was we cut it up into subintervals and we found the areas of each rectangle. And the base of each rectangle was a delta x. And we found delta x by doing b minus a over n. Okay. And then the heights of the rectangle were the heights of the functions. Okay, at different endpoints, f of x of I. And we multiplied them, and we added them up, and we did infinitely many of them. Okay, we said let the number of rectangles approach infinity. And that ended up giving us our adorable little Riemann sum and then our definite integral, right? So our integral was the integral from a to b of f of x dx. Okay. So it's important to have that as a baseline when you're talking about properties. Okay. The first property I want to talk about is what it's going to look like when we have the integral from a to a of f of x dx. What does this integral mean? What's it asking for? The area under what function? F of x from where to where? From a to a. What's the area if I start and stop at the same spot? There is no area. What's my value of the integral? 0. Okay. So my first properties. Okay. Next up, if I have the integral from a to b of a constant times my function. So what happens if I have y equals 2x instead of y equals x? My y values are going to all double, right? And the y values represent which parts of my rectangle? The heights. So if my heights are all doubled, what am I going to do to the area? Double the area, right? Or if I have a y equals 3x squared instead of a y equals x squared, the y values are all tripled. And so the area is going to triple. So when I have something like this, it's just going to be the constant times the area, the integral from a to b of f of x dx. Okay, the next one is saying if I have a function that's less than or equal to 0 on the interval, what does that mean for f of x to be less than or equal to 0? It's going to be below the x-axis. What does that mean for the y values? They're negative. When I'm constructing my areas, I'm literally doing the heights of the function times the bases. So if now all my inputs for my heights are negative, what's it going to do to the integral? It's going to give me a negative answer. Okay? Now, I understand that that concept is confusing because we've been calling it area, but the integral comes from something, and it's not perfect. So the formula that we use, or the formulaic approach that we use to figure out what what the integral is representing, is literally taking values for the heights of the function times the bases. And if those values are negative, it's going to give us a negative value. Bless you. Okay, so let's see how that can, let's see how that can come into play. All right, so let's look at the integral from -3 to 0 of y equals x. Let me try that again. Let's do the integral from -3 to 0 of x dx. All right, and again, we're just going to graph this. So my function is y equals x. Okay, and I want the area. Now, when we say under the curve, we're talking about between the curve and the x-axis. Okay, so from -3 to 0, between the curve and the x-axis, that's this region in here. Okay. So the length of, I have a triangle, right? The base of the triangle measures, the base measures 3, right? Because when we calculate that base, it's right endpoint minus left endpoint, so the base still measures 3. The height, however, is going to be taken with a -3. Right, so my area is 1/2 base 3 times height -3. You could think of it that way, Or you could just say, hey, my area of my triangle is 1/2 base height. Base and height both measure 3. However, because I've got a region that's below the x-axis, the value to that integral is -9/2. Okay, so you could, it doesn't matter where that negative comes in as long as it comes in. You guys see what I'm saying? Like, you can have it in terms of the height, or you can just recognize that it needs to be there and throw it in after the fact. Okay, good? How about this one? What's going to be the value to the integral from -10 to 10 of x cubed dx? This is not a function that we know how to integrate just yet, but if I think about what y equals x cubed looks like, such a great picture, fantastic, then I'm talking about an integral from a negative x value to its opposite corresponding x value. What's going to happen to the area between the curve and the x-axis? I'm going to end up having is I'm going to have equal areas below the x-axis and above the x-axis. And so you'll have equal negative values to positive values. And so the value of this integral is 0. I don't need to know what the actual area components are. What this integral is going to yield me is 0. Okay, so the integral is imperfect. It doesn't always give you true area. Sometimes it tells you that the area, like if I was going to plant a garden in my backyard, maybe I already have, that looks like this shape, and I ask you guys can you guys picture flowers growing in here? Isn't that beautiful? Okay, that's my garden in my backyard. I'll add some tomatoes among the flowers. I'm going to need topsoil, right? It's not like I can say, oh, I don't need topsoil if I do it this way. No, I will see later on that we're going to have to deliberately fix our integral to give us true area. Okay? Right now it's limited. It can do what the integral can do, and we have to understand the implications of that. Back to my properties. Okay, if we take the integral from a to b of f of x dx and add on the integral from b to c of f of x dx, where a is less than b is less than c, all you're doing to this is saying, here's my function. I want to go from a to b and then also go from b to c. So you're going to take this area and that area. What is this going to give me? The integral from a to c, good, of f of x dx. Okay, so I can add on components of an integral. Okay. I can also subtract off components of an integral. All right, so let's look at that in action. If I tell you that the integral from 0 to 2 of f of x dx equals 5 and the integral from 2 to 3 of f of x dx equals -2, then the integral from 0 to 3 of f of x dx is going to equal 3. So it would be the integral from 0 to 2 of f plus the integral from 2 to 3 of f. So I do my 5 plus my -2, which is going to give me my 3. Okay? Nice and easy. Here's another take on this. If the integral from 2 to 6 of g of x dx equals 8, and the integral from 3 to 6 of g of x dx is 2, find the integral from 2 to 3 of g of x dx. And again, I have no idea what this curve looks like. I don't know what's above and what's below. But if I go from 2 to 6, that whole area measures, and I'm using area in air quotes, okay, because it's not strictly area all the time, as you guys are already starting to see. Okay, so if that integral yields 8 from 2 to 6, and if I integrate from 3 to 6 and I get a 2, what's happening from 2 to 3? You just subtract them, right? So it's going to be the integral from 2 to 6 minus the integral from 3 to 6. And that would give me the integral from 2 to 3. So I'd get 8 minus 2, which is a 6. Okay? So you could do more with that property than I initially let on. 2 more properties to add to the list. First one's a property not too far off from our properties of derivatives. It tells us how to handle when I have the sum or differences of functions inside an integral. And just like with derivatives, when we're able to take just the derivatives of the individual pieces and string them together, it's the same thing here. Okay, so it would be the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So whatever function was happening there. Okay, so that means that if I know their components, I can combine them, or if it's simpler to work on them separately, I can work on them separately. This only works for addition and subtraction. Okay, this cannot work for multiplication or division. Okay, some of the benefits to that. If you're given something like the integral from negative 2 to 2 of the absolute value of x plus 4, you can graph the absolute value of x, shift it up 4 units, and then look at the area underneath the curve, meaning between the curve and the x-axis. Or you can say, hey, this is the integral from negative 2 to 2 of absolute value of x, plus the integral from negative 2 to 2 of 4 dx. Okay, and then treat those both separately, and then you're looking at the components instead of the big picture, but you get the same answer. So if I do absolute value of x from negative 2 to 2, I'm going to do 1/2 base height plus 1/2 base height, because everything's above the x-axis. Everything's positive. And then on this one, I have this little square here. So the area is going to be, bless you, base 2, height 2. I'm sorry, base 4, height 4. Base 4, height 4 on that. As opposed to trying to figure out what absolute value of x looks like shifted up 4 units. Which would look like this, which some of you guys would see this and get totally freaked out by that picture, or some of you guys would see it as 2 trapezoids and not get freaked out, or some of you guys would see it as 2 triangles sitting on top of a rectangle. But a lot of students find this breakdown and seeing it as separate geometric pieces as more helpful than the solid unit. So if the solid unit, if you try to graph your function and it makes you feel sad inside, then look at its components, okay? If you can. My very last property, it focuses in on the bounds, the limits of integration. And it talks about the relationship between the function. When the function does not change whatsoever, but I flip my bounds. So instead of going from a to b, where a is less than b, right? This is how we initially defined our integral. A is less than b. I'm now going to go from b to a. When trying to figure out this relationship, it's really important to remember where that a and that b really come into play when we're finding our integrals. And the integral comes from finding what again? That's what it means, but what is it? It means net change of the original function on the interval. But where does, when we found this integral, it came from doing what? It was very crude. What were we doing? That's why I had you guys do that. So it's important to understand that the integral is coming from the areas of rectangles, right? So the heights of the rectangles, the bases of rectangles. Our very first identities, we were talking about, properties, we talked about what happens when you change the height. If the height is positive versus negative, or if you double the height or triple height or whatever. Now I'm talking about the A's and the B's, which play into which part of the rectangle? The base, right? The bases of the rectangles. The bases of the rectangles we said measured delta x, right? And delta x we got by doing right endpoint minus left endpoint divided by the number of subintervals I use. Okay? And when we did that, we had the integral from a to b of f of x dx. Okay, and this dx comes from this. So now if I flip my bounds, what's happening to my base, my delta x? It becomes a minus b over n. Okay? And what's the relationship between b minus a and a minus b? Okay, so they're opposites. So if I'm taking my delta x, I'm making it where it was positive, now negative, or if it was negative, now positive, I'm making it its opposite. What's that gonna do to my integral? It's gonna make it opposite. Okay? So if I flip bounds, I'm gonna get an opposite answer. Right? And it's important to know, like, just in terms of understanding the properties of integrals, if I ever see the bounds flipped, it's going to make my answer opposite. But you're also going to see when we get into later stuff, if we ever come up on an interval, because anytime I see an integral from 2 to 0, like, I don't want it from 2 to 0, I want it from 0 to 2. I can switch it back to 0 to 2 as long as I negate the integral. Okay? All right.